Welcome to Mark's Tech Talk. In this edition, we're going to be discussing Thevenin equivalent circuit, Norton equivalent circuit, and maximum power transfer theorem. You'll recall the Thevenin equivalent circuit is a procedure where we develop a equivalent circuit that will be somewhat simpler to the original and is exactly the same from the perspective of the load. So let's look at the procedure, just recap the procedure a little bit. And this is very, very similar to what we would have done in a DC circuit. The only real difference is we're replacing R with Z. So procedure is open the load terminals, determine the voltage across those open terminals, that becomes your Thevenin voltage, and then determine the impedance viewed from the perspective of those open terminals with the sources removed. If it's a voltage source, replace it with a short. If it's a current source, replace it with an open. That assumes that you're dealing with ideal sources. So I think this will make a bit more sense when we look at a concrete example. So let's say we have this circuit and we want to find the Thevenin equivalent. Notice first off that the capacitor, we've already converted that to capacitive reactance. So we've kind of skipped that first step of converting from capacitance to capacitive reactance, and that's what's given here. So we want to find the Thevenin equivalent of this circuit, and once we do that, we'll find the Norton equivalent and the impedance for maximum power transfer. So the first step is to remove the load resistor. In this case, that will be the 200 ohm resistor. So there's the circuit without the 200 ohm load resistor. And the next thing we're going to do is to determine what is the voltage across those open terminals. We'll call it VL here. So how do we determine VL? Well, if we look at that circuit, what we're really looking for is the voltage across the 300 ohm capacitor, because the resistor has no current flowing through it. Therefore, there's no voltage drop. So the voltage across the load terminals will be the same as the voltage across the capacitor. So the voltage across the capacitor, which is the load voltage or the Thevenin voltage, is the source voltage multiplied by the impedance of the capacitor divided by the total series impedance. So the capacitor is 0 minus J300, and then the 400 and 300 are in series, so that would be 400 minus J300. And we'll multiply that by the source voltage, and when we do that, we get a voltage of 9 volts at an angle of minus 53 degrees. That becomes our Thevenin voltage. So now we have Thevenin voltage. The next step is to find the Thevenin impedance. So that's the impedance looking in from the load terminals with the load removed, with the source removed. So in this case, it is a voltage source, so we replace it with a short circuit. And you can see that on the left here, we have the source removed. So what is that impedance looking in from the load terminals? Well, we have the 100 ohm in series with a parallel combination of the 400 and the 300. So 100 plus J0, that's the 100 ohm resistor, is in series, so we add it. And then we have two parallel branches. Remember, there's a choice which way the current will go. That means parallel. So the 400 ohm resistor is in parallel with the 300 ohm capacitor. So we're going to do product over sum. 400 minus J0 multiplied by 0 minus J300. Divide by the sum of both of those, and that becomes trivial. Add the real parts, get 400. Add the imaginary parts, get a negative J300. So when we do that arithmetic, we find out the Thevenin impedance is 244 minus J192. Now, for impedance, particularly for Thevenin, it's very advantageous to express that in rectangular form. And that is because once we actually draw the circuit here, we have to break that down into a resistance and capacitance value. So the resistance is the real part, 244 ohms, and the negative imaginary implies it is a capacitor with a capacitive reactance of 192 ohms. And then we previously found the Thevenin voltage of 9 at an angle of minus 53. So this is the Thevenin equivalent circuit. This circuit will behave the same as the original circuit from the perspective of the load. All right, if we want Norton's equivalent circuit, it turns out the Norton impedance is exactly the same as the Thevenin impedance, so that doesn't change at all. The only thing that changes is we draw it in parallel rather than in series with the source, and we're changing the source from a voltage source to a current source. And the value of the current we determine by using Ohm's law. V Thevenin divided by Z Thevenin gives us I Norton. So in our example, I redrew the circuit. I have a current source in parallel with our Norton Z. The current, again, is simply Ohm's law, the 9 angle minus 53, divided by the Z, which is 244 minus J192. That gives us a current of 29 milliamps, an angle of minus 15 degrees. And the resistance remains the same, as does the capacitive reactance. So that is our Norton equivalent circuit. Now, if we want maximum power transfer theorem, remember from DC, the load resistor should be the same as the Thevenin resistance. Well, in the case of AC, we're going to use impedance, and we say that a load impedance is equal to Z Thevenin star. And the star implies complex conjugate. So we're looking for the complex conjugate of the Thevenin. It turns out to get the complex conjugate, all we have to do is change the sign of the imaginary portion. So the minus J192 becomes a plus J192. Okay, that's all complex conjugate means. It's just changing the sign of the imaginary portion of the number. If we had written that number in polar, we would just change the sign of the angle. So now we know the load should be 244 plus J192. So we'll draw that here. There's our original Thevenin circuit, and we have the load there, a resistor, and this time an inductor because it is a plus J. So you always have the opposite type of reactor in your load compared with your Thevenin. So the values, again, the resistor doesn't change, just like we had in DC. The load resistor is equal to the Thevenin resistance, and the reactance has the same magnitude but opposite sign. So in the Thevenin we had a capacitor, in the load we're going to put an inductor, and those two actually would cancel out if you were to analyze that circuit. So that is the impedance for maximum power transfer. Let's look at another example. Here's a different circuit. We want to find the Thevenin equivalent of this circuit. And just like before, we found the reactances already. Instead of giving you the capacitance and the inductance, I just gave you the capacitive reactance and the inductive reactance. I assume at this point you know how to do that. So let's find the Thevenin equivalent and the Z for maximum power for this particular circuit. We already have the load resistor removed. So next thing is to find the voltage across the open load terminals. And that process would be simplified if we simply combine that 3K capacitor with the 4K resistance and get the total Z of that. And I did reciprocal of the sum of the reciprocals. If you did product over sum, you should get exactly the same value, 2.4K angle minus 53.1. So I'm going to combine that into simply a Z there and say that Z is 2.4K angle minus 53. Now that I have the Z, I want to determine the voltage across those terminals. So just like before, the 5K and the 6K have no current. So all we have to do is find the voltage across that 2.4K impedance. So using voltage divider, we have the source voltage multiplied by the Z we're measuring across, divide by the total Z, which would be 2K plus J0, plus the Z we just found of 2.4K angle minus 53. And I know we're mixing polar and rectangular formats here, but with a calculator that is not a problem. You should be able to calculate that quite easily and find the Thevenin equivalent voltage of 12.2 volts at an angle of minus 24 degrees. That becomes our Thevenin equivalent. Now, in order to find the Thevenin Z, we look in from the load terminals, and of course that load is still removed. So now we have the 5K and the 6K in series, and we have the 3 and 4, and also the 2K are all in parallel. So the formula for the Thevenin impedance here is the 5K plus J6K, that's in series, and we add that to the parallel combination. Well, we have 3 branches, so we can't use product over sum, but we can do reciprocal of the sum of the reciprocals. First branch is 2K plus J0, then the capacitor is 0 minus J3K, and then the resistor is 4K plus J0. And again, a calculator should allow you to calculate that value as being 8.22K and angle of 42 degrees. If you convert that to rectangular format, that is 6.1K plus J, 5.5K. So we'll redraw the circuit. This time we have the source and a resistor and inductor in series. The resistor 6.1K, that's the real part of the rectangular format. And the imaginary part is 5.5K. It's a plus J, so it's an inductor. And the voltage we previously found is 12.2 angle minus 24. So this is the Thevenin equivalent circuit. You have to draw the circuit and add the values. Don't just give the values. You actually should draw the circuit also. So now that we have that equivalent circuit, how do we find the Z for maximum power transfer? Well, again, we're going to have a resistor along with a reactor. The reactor will be opposite of what we had for the Thevenin. The Thevenin is an inductor, so the load should have a capacitor. And of course, the voltage just carries through. The load resistance is what we found, 6.1K. That should match the Thevenin. And the load capacitance, the magnitude, should match the Thevenin, but the sign is opposite, so we change from an inductor to a capacitor. So hopefully that gives you an idea of how to do Thevenin equivalent circuits in AC. Hope you enjoyed the video. Stay tuned for more.